Water and carbon dioxide. Write down the combustion of heptane. Go. You have like 30 seconds. That means you know you're organic and that's what I mean. Halfway to your computer, you don't need your computer anymore for the time being. Thank you. Halfway to your computer, you do not need your computer for the time being. We're trying to save the battery a little bit here. Alright, what's hep mean, Bryce? 7, and heptane would mean what? So 2n plus 2, so what's the whole formula for heptane?
2, 7 plus 2.
So C.
Oh, C16.
No, so hep is number of carbons. Okay, so how many carbons? 7. And then H is the 2n plus 2. So 7 times 2 is 14, plus 2 is 16. All right, everybody, this means reacts with what?
Oxygen.
How do I write oxygen?
O2.
O2. And you guys said make CO2 in water. How do you start balancing this?
Start with the C's.
Start with the C's. What do I need?
7 in front of CO2.
7. And what do I need in front of hydrogens?
8.
Or water? 8, because 16 is over there. 8 times 2 is 16. How many total oxygens do I have here? 7 times 2 is 14. How many here? 8. Hallelujah. This thing is not odd. This is even. What's this number? What is it? 22 oxygen. So what do I need here? 11. Good. All right. Combustion of copper 1. Write some paper about your groups. I'm going to go ahead and let you guys do the next 3. Don't forget to balance it, guys. Alright, come back to me. 3, 2, 1. Combustion of copper. Copper 1. Lumineers table, get me started. Good, Ce plus O2. You didn't get distracted about that 1 up front. Thank you, because we do not write the charge up front. It's only going to be utilized in a crisscross fashion. Makes what? So Cu2 plus, or Cu2, good. So copper had a 1 plus charge, and oxygen always has a -2. Crisscross, this is copper 1 oxide. It still is the name copper 1 oxide. And then I need to balance this out. What do I need, guys? Somebody else? Good. Okay. Lithium carbonate reacts with iron. Everybody, lithium carbonate. Li2 CO3. Good. Reacts with Fe. Do I put the 3 plus here? No, it's just solid iron. And what do we get?
Right now.
All right, thank you. So what do we say this is? No reaction. Good. So you're looking at, see, iron and lithium. Those are your two metals you're looking at. Relatively, where's lithium versus iron on the activity series? Lithium's where? It's top dog. It's like, I am going to react whether you like it or not. I'm going to be in a compound, people. So it's already in a compound. So if iron tries to switch, it's like, nope, you're going to stay out in the cold. You're not gonna switch with me. So therefore, if it's not active or reactive enough, therefore we put NR to indicate no reaction. Do still put the front stuff. That way you're thinking about what kind of reaction this is, aka single replacement. Calcium chloride reacts with lead 2-chlorate. What kind of reaction is this? 5 types. What type? Double replacement. It's easy to see because you have two compound, or an ionic and an ionic reacting. So what's the formula for calcium chloride, everybody? CaCl2. Corbin's table pick up from here. Corbin's table pick up from here.
EbClO.
2. Lead 2, chlorate 1, crisscross. CJ's table pick up from here. Somebody. So you're making lead, which is the positive, get with the anion of the other. Okay, so PbCl2 is that's still lead 2 chloride. And then Aiden's table. Aiden's table, Estes, Jacob, or Amir.
CaCl.
Ca.
Cl.
2. Good. So we're re-crisscrossing on both products. And then from this one, we have to consider the what rules? The what rules? Solubility rules, right? So we need to look to see if this reaction is occurring because we're looking to see if it makes a what? Is it going to make a precipitate? So the single replacement series, the way we look at that is to see if the activity series allows for the reaction to occur. With double replacements, we can write it on paper. That's just la-la land right now. We need to see if it's going to actually work to see if there's a precipitate or a chemical change occurring. So I look at the what part to look for the precipitates. The anions, the chlorides and the chlorates. Chlorates are not on your solubility list, right? So then who do you ask for that one? Me. I have to tell you. So chlorates are always soluble 100%. So what do I write here next to calcium chlorate? AQ to indicate it's aqueous. It's soluble. It's going to dissolve. Okay, so far that doesn't help us too much. Chloride. Looking at chlorides, everybody, what's the general rule for chlorides? Soluble. That means aqueous, right? Then we read the exceptions. And what do they say? Lead needs exception. So what do I write here?
PPT.
Either PPT or downward facing arrow or solid, something like that. So does this reaction occur? Yes, and it's already balanced, so we're good to go. Okay, so that's a quick review. I'm expecting that you're able to do this on your own at this point and try not to use your full bowl as much as you maybe want to. Okay, so we're going to talk about something called NIEs, net ionic equations today, and that's just really an expansion of double replacements, and then we're going to work on a pre-lab. We have 2 labs this week, tomorrow and Wednesday. Okay, so wear shoes. When it's getting nice outside, but wear shoes. Okay. So I'm gonna discuss this with some folks after I get the rest of us on the same page. Okay, this is the big boy slide for the day. It's the most detailed of the slides, but then we're gonna go through examples. So I'm gonna be quiet. You're gonna write some information first. This is kind of like your guideline on how to approach NIE, net ionic equations. If you cannot see, there's a seat right here, and then you can also feel free to move. I think the detailed nature of these steps is worth it. That's why I'm letting you try to take a minute to write down everything you need to. And then we're going to kind of dumb it down to a really narrow set of steps. Raise your hand if you are in either an extracurricular activity like athletics or theater or band or dance or clubs. Okay. So we got some, most of us are participating in something, right? Something that matters. So baseball is included right now, right? Raise your hand if you're baseball. Okay, so I got 2 baseballs. So we go and watch you guys play, right? We're watching you guys make something happen, make plays happen, you know, hit foul balls, hit home runs. We're watching you. What do the people call it in the audience? Spectators, right? Okay, so they're watching. Are they doing anything with the game? Really? Are they making stuff happen? They're just yelling at people and going, woo, go, Chandler, right? Whatever. So they're just spectating. So that's essentially what we're talking about here. We're talking about a reaction, and there's only a couple of ions in the reaction that actually are the main players. They're the ones that are making something happen, making a chemical change happen. And those are the ones that make a precipitate. Truly, the ones that make a precipitate are the only ones that matter. So if we're trying to narrow down the reaction to like really what matters, we want to cancel out all the nonsense. We want to cancel all the spectators. Therefore, we call those spectator ions because we want to get them out of the equation. So we're only looking at the ones that actually are doing some damage, actually making the reaction happen. So that's what this whole idea is, making the reaction look like, making the reaction include just the ones that matter. So we're canceling out the spectators of the reaction, the ones that don't do anything, they just watch. So here's your steps. 1, BC. What's BC stand for? Thank you. Get your balanced chemical equation first. Thank you. And then with that, you're going to get your solubility determined, and you're going to use the solubility rules to determine those precipitants and aqueous species. 2, you're only going to split the what ones? The soluble, the aqueous. So if we can't remember soluble and aqueous are the same, this might help you kind of dumb this down. Only split the aqueous things. Okay? And once you split the aqueous things, what are you looking for? What are you looking for? You're looking for spectator ions, but how do you know they're spectator ions? They are the literally exact same from beginning to end. So cancel same reactants and products. RMP, reactants and products. Once you canceled out the same reactants and products that are literally exactly the same from left to right, you then have your NIE. You have your net ionic equation, and that's it. Whatever's left is your NIE. So this will make much more sense when we do this example out and to give you what this looks like. But I'm going to show you a video first that will actually walk us through it. Write down everything this man is writing. Not everything, but write down everything he is indicating for the reaction, and I'm going to do the same. Okay? So I gotta start at 4:30. Yeah. I want to get that Gonna want to cut those captions. Okay. All right, you guys ready? Writing down the reaction he's writing down. Here we go.
And to make measurements. But now let's go to an aqueous reaction. And so in this reaction, we're taking lead nitrate, which is clear, and we're adding it to a solution of potassium iodide, and it produces a yellow precipitate. And so what we're getting is a solid that comes out of that. And so I could observe that. I could know what those chemicals are, and then I'm going to write it out. And so we've got a solution of lead nitrate, solution of potassium iodide, and it's making a yellow precipitate of lead.
Okay, so he means lead 2 nitrate, break down lead 2 nitrate, and potassium iodide. Those are reacting, sorry, I know it's dim in here. And they produce lead 2 iodide. And then what else does it make? No, that is yellow, the yellow precipitate is lead 2 iodide and potassium nitrate.
Lead iodide that settles to the bottom. Next thing I want to do is I want to write out my reactants and products. Now, if you don't know how to go from the name of a chemical to its equation and vice versa, I'll put a link down here to a naming molecules or a naming compounds video that should help out. So the first thing I want to do is I want to write out all the reactants and products. So now we've got lead nitrate, potassium iodide, making lead iodide and potassium nitrate. Next thing I want to do is I want to make sure that I balance it. And so I can see right here that I don't have enough iodine on the left side, so I could add a 2 there. Now I've got too many nitrates on the left side, so now I can balance it like that. I also have to write the state that it's in. So remember, those first two were aqueous, but this lead iodide is going to be a solid. And now I've got a nice molecular equation. But again, this video is about 2 other equations. We've got ionic equations and then net ionic. And so how does that work?
All right, so how did he get S here? How did he call that out as a precipitate? Because what? Where would he think he maybe accessed some information about this? The solubility rules. Now, some of us, you're going to find that you accidentally memorize some. Iodides, chlorides, bromides. Basically, your suspicious guys are always lead, mercury, and silver, lead, and mercury. So a lot of times if you see lead, be very suspicious of it and look at your solubility rules because that's likely a precipitate, except with nitrates.
What is an ionic equation? Well, if you think about this lead nitrate right up here, it's not sitting in that solution as a connected molecule. Remember, it's going to break apart into its ions. It's going to have its lead ion.
So this is the piece where we said, okay, everything aqueous, we're going to do what? We're going to split them. All those aqueous ions are not going to be ionic anymore. They're going to be separate ions. So he's splitting them, and we're going to rewrite the charges.
And nitrate ions, and those are going to disassociate from one another. Those are going to separate from one another. And so when I'm writing out an ionic equation, what I have to do is I have to write out all the ions. And so let's do that one first. I'm going to have that lead ion, which has a 2+ charge, and then 2 of those nitrates, which have a 1- charge. Now, why am I writing a 2 here? Because we have 2 of those nitrates. And so you can see in an ionic equation, what I'm doing is I'm busting apart each of those ions. Let's go to the next one. So that potassium iodide, I'm going to break that apart into its 2 ions as well. You can see that I'm writing that this is in solution, so it's aqueous. Next, we get to the lead iodide. Now, remember that lead iodide is a solid. It's that yellow solid. And so I'm not going to bust that apart into its ions. I'm just going to write that as lead iodide as a solid.
So only the aqueous ones we're splitting into their ions that they're comprised of. And we are indicating the coefficients because there might be more than one of those ions in the compound. So lead, there was only one lead 2+. Nitrate, there was a subscript of 2 on the outside indicating 2 nitrate ions. And then in front of potassium iodide, we have a big old coefficient of a 2, so we must indicate there are 2 of each of the ions inside of potassium iodide. So that's 2 K pluses and 2 I minuses. Good so far? Okay, we'll do another example, no worries. And then he said, nope, you're not aqueous, we're keeping you as is, don't touch this.
But then this potassium nitrate is going to break apart into its different ions, so I'm going to write it out like that. So I know that's a lot of work, but this is a complete ionic equation. Why is that important? It really allows us to look at what ions are in that reaction. And so if it's ever an aqueous reaction, lots of times we'll use this ionic equation. Sometimes they'll call it a complete ionic equation because it's showing all of the ions that we have present. Okay, what's the...
Okay, so now discussing your groups, who do you think are going to be our spectator ions, meaning the ones that don't do jack? They're sitting there looking pretty from beginning to end.
Nitrate. Potassium.
All right, Ron, give me one of them.
Nitrate.
Okay, I heard nitrate. Good. Nitrate. There's 2 NO3 minus, 2 NO3 minus. Those are exactly the same. And potassium, 2K plus, 2K plus. Who is actually involved in the chemical reaction? Lead and iodide, right? They were separate, and then boom, they precipitated. Those are the only 2 guys that are playing in this game. That are only 2 that are participating in the precipitation.
Third type of equation, that's going to be the net ionic equation. So if we look back at this equation, you can see that we have 2 nitrate ions on the left side, and we also have 2 nitrate ions on the right side. And so they're really not being changed in this reaction. And so we call those spectator ions. They're really just watching. And so what you can do is you can cross out things on the left side that are also found on the right side, as long as they're in the exact same form. Can you find something else on the left side that's also on the right side? That's going to be those potassium ions. So I can cross those out as well. And so once I've crossed out all those spectator ions, I can write it out like this, and that's going to be my net ionic equation. So that's really, it's just showing what atoms are part of this chemical reaction that are actually forming these bonds. And this will become important when we're looking at redox.
Don't worry about redox reactions. Okay, so the NIE, net ionic equation, only includes the reactions that matter. I mean the reactants that matter. Okay, so this is a picture just to kind of show you what's happening. It's a little small. Let me see if I can make this bigger. So you've got, this is an ionic structure, and you put it in a solution. And in this solution, you have the spectator ions of sodium ion and chlorine ion, and then whatever was in the solution has, oh no, sorry, not this one. Whatever's in solution started to dissolve. So that's a true fact. It has started to dissolve. This is a little harder to see. But we have Ag plus and NO3 minus. Who's that? Silver nitrate. It's soluble, so it's broken apart into the ions that it's comprised of. And we have NaCl, so we have sodium chloride, right? So these are the 2 aqueous reactants. Notice that they are 100% soluble, therefore they're separated. And then as they reacted, silver chloride started to do what? Therefore it's forming a precipitate, and who's floating? Sodium ion and nitrate ion. So who are the spectators? Sodium nitrate, and the main players are silver and chlorine, making silver chloride. So that's what we're looking for in the lab. We're looking for precipitates form, but we know precipitates forming are only usually with 2 species, because they make 2 ions come together. All right, so we already did the first one. You guys did the second one. Walk through the whole process. BCE, ionize, cancel. Okay, do magnesium chloride and sodium phosphate. Work within your groups if you need to. Because once I do 2 of these, you should be fine. You should know your steps. Have a periodic table nearby, because I know you haven't memorized this thing. You don't need to. Looking over your shoulder, so I'm going to look at your BCE initial so I can give you feedback if you need it. a nice little cheat sheet. All right, let's check our BCE together. Some of you guys are already done. I'm going to help process with the rest of you as you were there. So MgCl2, thumbs up. Let's go. Na3PO4. We finally got phosphate. I think a couple of us. I was trying to get you guys to do that in your own. And then you double replace sodium chloride and magnesium phosphate, Mg3PO4 form, and then balance it out. You need a 3, a 2, a 6, and a 1. Now, you could have written yours in opposite order here. It does not matter. It's just tomato, it's the same. All right, so assuming that most of the time these are two aqueous solutions that are coming together, and our job is to predict the products, assume that your reactants are always aqueous. So put AQ here, because if not, it's hard to add things together and they're not in their solution form. So we're pouring two liquids together, boom, what do we see happen? Have you guys figured out solubility rules here? Okay, so two liquids go together, boom, what do we see happen? Who's precipitating? Magnesium phosphate, right? So all phosphates are insoluble, aka precipitates, except for alkali metals and ammonium, right? That's what the rules say, so that's not the condition here. These are going to stay as precipitates. And then all chlorides are soluble, really, only exceptions are those heavy metals, silver, lead, and mercury. So this is aqueous. All right, so who has to stay together when we do our ionization process? Magnesium what? Phosphate. So I'm going to put a little square around that so I don't touch this. Okay, so these are all aqueous, therefore we split. So what does this break into? How many Mgs? 3 of them, because there's a coefficient of 3 that distributes out. So there are 3 magnesium 2 pluses. I'm not putting aqueous, but let's assume every ion is aqueous. And then, so that 3 distributes there and there. So what else is made? 6 what? Chlorine ions, right? You do have to distribute your coefficient. And then what's made here? Good. 2 times 3 is 6 what? Sodium ions. I need some more help here. I got 2 people helping me out. What else is made from that? Good. 2 phosphates. Keep the phosphate together. Do not break it up. It is a happy family, and it's going to also have a what charge? 3 minus. Anytime you're breaking them into an ion, they must have charges. If you just put the symbol, it will not be correct because it's a totally different compound. So that produces aqueous sodium chloride, which makes what? 6 sodium ions and 6 chlorine ions, because that's from each of the 1 and 1, but a 6 coefficient applies. And then what do I do with this? I just write it down, right? Mg3PO4 2 precipitating. All right, guys, who's saying exactly the same from left to right? No, who's saying exactly the same, meaning they are identical in reactant form and product form? Sodium ion and chlorine. Good. There's 6 chlorine ions. There's 6 chlorine ions. Cross those out. Those are canceled as spectator ions. And then there's 6 sodium ions and 6 sodium ions. Cancel those out. Who are the main players in this game? Not only just magnesium, but 3 magnesium ions and 2 phosphate ions. They play, and they make what happen? It makes a precipitate. Good. Magnesium phosphate. So what I'm circling here will be called your what? Net, right? Your net ionic equation, your NIE, which is just the overall equation once you've canceled out spectators. Give me a scale of 1 to 10. Where are you at on this? Just I want to see where you are. All right, so I want to practice a couple more with some folks. I'm not going to bore the rest of us to tears if you're good to go. So this is where we're going to kind of break into 2 groups to work on separate things. So pay attention so you know which group you're going to be in. I'll do more, but I think if I give you a chance to practice, you'll be fine. Everybody pull up this bit.ly address first, so I can show you what you're responsible for. made it public. Let's make sure I did that. I already closed it. It's also under homework, so do not fear. It's there for you. All right, so what we're doing on Wednesday is this shortened replacement reactions lab. It's just a couple of reactions, but you know, it's nice to be able to put a face with a name, actually see what's happening when we're talking about all these reactions occurring. So what you're responsible for doing are writing the BCE and the NIE for 1, 2, 3, 4, 5 reactions. And those 5 reactions, I'd like for you to organize that in a table form. So you can write like the molecular or the BCE normal. Your choice. You have to decide if that reaction will occur or not. So what are you looking for here? Solubility, right? You're looking at solubility. And then observations you can't do yet because that's like the actual lab observations you'll be making. So you could leave that empty. And then you'll obviously need to write the NIE based off the BC. And you know your steps for that. So if all of your work is done, like 100%, you got PS 11, number 12 done, you don't have any makeup work from last week because you were out. If everything is done, please work on this right now because this is technically homework, but I wanted to give you some time in class to work together because I know that this can be a little challenging. If you have other things to do, 1, prioritize number 12 on problem set 11. Okay, that is your priority because I need to check that today with you in class so I feel good about giving you a quiz this week. I need to feel good about that before I start to hold you accountable for information. I'd like to give you a chance to check over some information. So, you know what you're doing? Thumbs up. If you're working on this, then you may sit at a lab to work with a partner, if you like partner of your choice, just so you can like have a colleague to talk with. Do not mess with my strikers. I already see you. I know you're going to be messing with those strikers. Don't mess. Okay, I'm going to give you guys about 10 minutes and see where we are.
Can I see my quest?
Is that from the bonding?
Yeah.
It's in the
I checked my brain. I just want to make sure.
All right, just gonna be productive, folks. Yeah. If you're in the back, please come back up to the front, and I want everybody to have either a red pen, marker, highlighter, something to scratch off the ones that you got wrong, so that you know that's where you probably need to go back and focus your study efforts on. So if you need something, holler, raise your hand. Oh, actually, lies. Go grab your marker. They're right there. Go grab your marker. And let's roll. I'm starting with if you are ready or not. Here we go. So my old problem set T had a couple of different reactions. I've switched some reactions since whenever I made those, so I'll have to ask a couple of you guys for that reaction so I can write the board. So lithium and oxygen, 2 elements. What kind of reaction is this? Binary synthesis, right? So if you can give me the descriptor with that, that would be great. Binary synthesis makes lithium oxide. What did we do to get this 2 here? That 2 right there. How did we get it? Crisscross charges. If you make an ionic species, you have to crisscross charges. B, magnesium chlorate decomposes. What kind of decomposes? What's like the type? Metal chlorates, and they always make what gas? Oxygen, the friendly gas oxygen. Leaving behind a metal chloride, and the metal chloride here is magnesium chloride, and O2 gas is our diatomic oxygen gas. And how do we get this 2 over here? Crisscross. How do we get the 2 here? How do we get the 2 here? No. Diatomic. It's just diatomic. All right. And next one. This was similar to your single. No, this is your single replacement reaction because you guys had some on Friday. Friday. We had metals and water, And I said, I think it's valuable to write water as HOH because then you can maybe see who it's trading with. So if you write water as HOH, sodium is looking to switch places with who? Right, these hydrogen, switching places with hydrogen because it's cations replace cations, right? So sodium has the potential to form a cation. H literally is a cation. When they switch, where are you looking to get that information if it's even possible? What sheet? Which side? Activity series. And sodium falls in the range of can replace hydrogen from water. So this will react, making sodium hydroxide. And where am I getting this 2 from? Diatomic hydrogen. How can I test for hydrogen gas? The flaming splint, right? And you put it in, and what happens? It makes a pop or a bark sound, like that. Alrighty. Nitric acid and calcium hydroxide. What kind of reaction is an ionic and ionic coming together? Double replacement. And so when we doubly replace, H gets with OH, calcium gets with nitrate. How am I getting this 2 here? Crisscross. And then water, HOH is water. And I want you to know that this is L, this is liquid. So whenever it says on number 12, now that you know what NIEs are, you can go and complete that process. If you make a liquid, this will be relevant for our lab on Wednesday, but if you make a liquid, it kind of acts like a precipitate. So think of it like a precipitate. It's not literally a solid though, so I want you to know that you do not split it up. So keep it together whenever you do your ionization process and go through your NIE. You good with that? You pick it up when I'm putting down? Yeah. Don't split it up. Okay. Moving on. Oh, this one. What did this one say? Ethane? Was it ethane? Okay. So I've changed this one since. So ethane, formula for ethane? C2H6 is combusting, so what's that mean to add? Oxygen always makes what?
Carbon dioxide.
And what's the balanced form of this? So I know you're going to put a 2 and a 3, and then you get 7 halves here. So let's just give me the final answer. This is 2, this is 7, 4, and 6. That's our combustion. So I think we've had single, double, synthesis, decomp, and combustion. We've actually had one of each type so far. Okay, how are you guys doing with predicting the type? Like of the 5 types? Which are the hardest ones to predict? Which ones are the hardest to predict? How are combustion? If you had oxygen present, you know to make carbon dioxide and water if it's a hydrocarbon. If not, it's just a metal synthesis. Single replacement and synthesis, I can see how you mix those. Okay. What was F? Fluorine reacts with what? Magnesium bromide. Okay, so how to write fluorine? F2 reacts with MgBr2. Okay. What kind of reaction is this? Single. So who are you looking to switch? F2 and Br2. You're looking to switch the nonmetals and nonmetals. Remember, the same thing has to replace the same thing. So can fluorine replace bromine? How are you figuring this out? You're not pulling on your butt. It's on the sheet, right? It's on the activity series. Fluorine, chlorine, bromine, iodine. Fluorine's the most active. It wants to bond. It wants to get with that magnesium. So bromine gets booted to the cold like this. 2 diatomic, and magnesium fluoride is also F2 because of crisscrossing charges. And it's balanced. Woo! Dang it, what was G? Copper 2 reacts with silver nitrate. What kind of reaction is this, guys? Single replacement. So who are you looking to replace? So you're looking to see if copper will replace silver. So that is the question. You're looking to see if the metal replaces metal. Is copper good enough? So copper's mediocre on the activity series. Silver's pretty low, right? So yes, it will replace. So what do we make? Copper what? Copper what nitrate? Copper 2 nitrate, CuNO3, 2, and silver. So what would this reaction look like? There's no gases, no fire. So you have some pretty copper metal. It's what color? Copper. It's copper color, right? Okay. So, and you have some clear liquid, and you mix them together, and you make the copper color go away, and you make pure silver. You alchemist, you make pure silver. I do this to make silver for a lab every year, and I feel like I'm the coolest person ever. Okay. No. No, just because it's got silver nitrate on it. Silver nitrate kills your cells, so it's not clean. All right, calcium and chlorine. What is the reaction here? Synthesis, making calcium chloride. Where's this 2 coming from? Crisscross charges. You're not just smishing them and going, yep, made some calcium chloride. I know that 2 looks like it's from this, but it's not. It's from crisscrossing charges. Sodium chlorate, single reactant. What kind of reaction does that have to be? Sodium chlorate is a single reactant. What does it have to be? Decomp, and this is a metal chlorate. All metal chlorates always make what gas? Oxygen. O2 is your gas of choice, and then the metal chloride is also produced, and it's a 1 and a 1 because there's a 1 and a 1 charge, and it's diatomic because it's diatomic. Moving on. I'm just double checking with those of you who are at this point. Oh, dang it. What was J? Was this the pent? Butane. Thank you. So what's butane? C4H10 plus oxygen makes always hydrocarbons combust to make what? Carbon dioxide and water. And what's our end game here? 4 and 5. No, that's going to be odd. So we get a 2. That's 13, right? That's a 8 and that's a 10. Thank you. Because there's 8. 8 times 2 is 16, plus 10 is 26, 13 times 2 is 26. Copper 2 chloride and sodium sulfide. What kind of reaction is this? Double replacement, and sodium gets with chlorine, and copper 2 gets with sulfide. Sulfide, is that on your solubility rules list? S? No? Okay, so I'm telling you now, this is a precipitate. Is it? Okay. I try to give you like the simplest one I could give you, but sometimes I put some more on there than what's on the list. So, copper has a charge of what? 2. Sulfur has a charge of? So we have the empirical formula here as 1 and 1. L, what kind of reaction? Oh, I forgot. Let's fix this real fast. Copper and iron 3 sulfate. What kind of reaction is this? Copper and iron 3 sulfate. Well, I know that. What type of reaction is this initially? Single replacement. So you're looking to see if copper will switch with who? Iron. So who's more active, copper or iron? Iron. So iron's like, nope, you're not getting with sulfate copper. You're staying where you are. So it's not. It's a no reaction. Who got that? I figured a very few because we're just so used to making these things happen. So do consider the activity series. Okay, couple more. Ni and O2, so nickel and oxygen, what's the only thing they can do? Combine and crisscross charges, right? We're making nickel 2 oxide. What kind of reaction would you consider this? Synthesis or combustion, right? Combustion of a metal, because it's got O2 in it, so it could be synthesis or combustion. Next one, sodium iodide and chlorine, what kind of reaction? What type? Come on. Single replacement. Who's trying to replace who? Look, yeah, it's non-metals trying to replace non-metals, so you got to be kind of wary of those. So you're looking to see, is chlorine more active than iodine? Is it? It's even the same like your table. Was chlorine above iodine?
Yes.
Yes, so it does replace, so it does get booted out. Iodine does get booted out. This is actually a solid, but it's okay. Not important. Question? Thank you. Balancing. Yes, thank you. All right, and how many more of these do we have? Oh gosh, okay. Calcium hydride. Ooh, who got that formula right? Calcium hydride. CaH2, crisscrossing discharges, good. And water. So this one's weird, but if you write water as HOH, I think you should be able to see this as a what style reaction? Right, this is a cation, anion. It is a double replacement. So calcium gets with hydroxide to make calcium hydroxide, and this H gets with the hydride H to make HH, H2, just hydrogen gas. Yep. So that's a double replacement one that was kind of funny if you didn't write water As HOH, it probably was difficult to see what style of reaction it was, but now you should see. I am going a little fast on this simply because one, you should have already had these done, and two, it's easy to check them once you have them done. So magnesium nitrate and potassium hydroxide, what kind of reaction? Double replacement, and with that double replacement, we make potassium nitrate and magnesium hydroxide. A lot of hydroxides are insoluble, and magnesium hydroxide falls in that category, so this should be a precipitate. And then lastly, lithium hydroxide and iron 3 nitrate make iron 3 hydroxide and lithium nitrate through double replacement. Which of these is the precipitate?
Wait, that's
Oh, is this your, sorry, I have down a Q. What was Q's on yours? Oh, sodium sulfate. I will switch this, sodium sulfate, so you guys make sodium hydroxide and lithium sulfate. Okay, so with this reaction, balances. Does that work?
Yes.
Okay, so balancing this, we're looking for species to be precipitating. Does the sodium hydroxide precipitate? Look at your hydroxides. Where are they on your list? Where are the hydroxides out on your list? Insoluble. But what are the exceptions under that? Alkali. Look, sodium's an alkali metal. So what do we write here? No, hydroxides are all precipitates except for alkali metals, and sodium is an alkali, so what do I write here? 8Q, because it's not in the insoluble category anymore, because it's an exception to that rule. And the rule for sulfates is what? All soluble except for a couple things, but lithium's not one of them. Okay, guys, we have a liquid and another liquid. We put them together, and what do we see? Liquids. What's happened? Nothing. So this is a no reaction. I know you wasted your life on that last one. Okay, so with this being our last minutes, I'm just going to announcements in 2 or 3 minutes. Look over the rest of the replacement reactions. You can at least get those 5 reactions down. Who's already basically done? We're just getting the 5 reactions, 5 BCEs. All right, full 15 minutes and not 5 reactions. Just seeing where we were. I'd like for you to finish problem set 11 because you're basically done with that except for writing NIEs from that particular set number 12. What are the only ones you're writing NIEs for on number 12 though?
Double replacement.
Only double replacement, and I think there were 5 or 6. Okay? So finish working where you want to right now. I'll have you guys put computers up in just a couple minutes. We got a lot done today. Good job, guys. Good job. Put it in the box.